Hi guys. So I'm going to talk to you about the Gravity Lab. Um, Hopefully kind of motivate it for you, give you an idea of how it works, and show you a little bit about the code so that you can tackle that lab. So this lab is a simulation lab using numerical integration. Um, so so far we've been looking at basically GMM over R squared, that equals MV squared over R. And we've talked about this in the context of some different situations, but for example, like a satellite around the Earth, you have a satellite or whatever, uh, and we've been able to use this to solve different kinds of problems. Um, like if they give you the radius, you can figure out the speed of the satellite, or if they give you the period, say, you can figure out, at what radius the satellite is orbiting, and etc. Now, those, we've been able to solve basically analytical problems. Now, in contrast, this lab is numerical. So let me give you an analogy to kind of get started. Um, Basically, imagine a plot of velocity as a function of time. Now, if you wanted to know how far you went in some amount of time, you would have to add up this velocity. You would integrate it. So in other words, the x would be the integral of velocity um, over time. And in this situation where the velocity was constant, this integration is really easy, right? The x is just v times t. Now, however, think about if your velocity is not constant. So imagine it's varying. The mathematical operation is the same. You would integrate this, except the velocity would be a function of the time. And you would need some way to figure this out. So if it was a function that you knew, you'd be able to do the integral. If it wasn't, though, if you just had this data, what you could do is you could divide the data up and you could estimate the area under the curve. And you could add up these little rectangles and you could numerically figure out what the integral would be. And you can imagine that estimate would look something like a sum, where you would add up these little average velocity chunks. So suppose like one of these is average velocity times some little step size in time. So now we would have some delta t for each of our steps. Here, let me write this a little more clearly. It would be delta t. And there might be some initial position too as you add these up. Your integral, if it was an indefinite integral, would have an initial position. Um, and that would be a way to numerically figure out the position, to figure out how far you've gone. And you might have encountered a more sophisticated version of this, like the trapezoid rule, where instead of using just little rectangles, you do a more complicated, a better approximation. Although if you're, depending on where you are with your calc, you may not have encountered that yet, and that's okay. We won't have to derive this or anything for the lab that we're going to do. I'm just talking about this because I think that this might be something that you're familiar with. Now, so what we're going to do for gravity is the same idea, except it's more complicated because we need to do this in more dimensions. So let's think about our situation here that I mentioned before. You have a satellite, some little satellite or whatever. Try and draw this neatly here. So while in this situation that I mentioned above, you just have velocity, it's just a one-dimensional situation. If we're talking about a satellite, an orbit though, this velocity would really have Vx, Vy, Vz. It's going to be in 3 dimensions. And then we would also have to worry about the position of the satellite in 3 dimensions. So you can imagine figuring out where that would be. And so instead of a one-dimensional problem, so this problem that we talked about before, our x, this is 1D. And we would find x, with this sort of sum. Now we're talking about a 6-dimensional problem because there are 3 velocity components and there are 3 position components. But I'm going to use the same variable or the same nomenclature. We'll call it x. And we're just going to put in everything in here. So we would have x, y, z, vx, vy, vz. Okay, so this would contain all the information about the system. So notice when we were doing this before, for each time step, we also needed the velocity. So we're going to need a general velocity that corresponds to this vector x that contains all the information about the system. And you can think of this as a for loop. So as we step through time, what we can do, as we step through time and add up the pieces, what we can do is the velocity that would correspond to x, we can use the velocity from the previous iteration of the loop. The velocity for y we can use from the previous iteration of the loop. Previous iteration. So let me be more clear here. Let's call this xi. So the velocity vector would be made up of the velocities that correspond to x, y, and z from the previous iteration of the loop. So you can imagine that being here. And then for the accelerations, we would need to use Newton's law of gravity. So the accelerations will calculate. So let me just say this is from the previous loop iteration. And this will use the law of gravity to calculate the acceleration. So let's be a little more precise about the law of gravity. What is that going to look like exactly? Well, what we really need to do here is look at this in the vector picture. So this vector that points from the Earth to our satellite we'll call RES. And let me add also, there's a unit vector that's associated with that. I'll call RES hat. And the law of gravity says that the force of gravity on the satellite is going to equal big G times the product of the masses. So the mass of the Earth, the mass of the satellite, divided by the square of the distance between them, times the direction, so RES hat, and then remember there's a negative sign because it's attractive. So the force that would be on the satellite, the force of gravity, let me put it actually in a different color, would be pointing towards the Earth along that line, and it would be given by Newton's law of gravity, and it would be in that direction. Make this blue. Okay. So if we want to find the acceleration of the satellite, we know that the force is equal to the mass of the satellite times its acceleration. We can divide out that factor of the satellite's mass. Now, being a little more careful about our vector notation, this acceleration will be given by negative gm over that distance squared times the unit vector. Now, in the code, what this will look like is actually slightly different. Rather than having this in terms of the unit vector, this will look like the vector between them divided by the magnitude cubed. And the reason that we can write it like this is, remember that the unit vector is a vector that it's a special vector that has a length of 1 and points in the direction of your vector. So the unit vector points in the direction of our from Earth to the satellite. But if you divide then by a factor of the length of it, this thing will have a length of 1. So I think one thing that can be difficult for us to understand is like, well, what exactly is a unit vector? This is another way to think about it, is as a vector divided by its length. Then you're just left with a vector that would have a length of 1, but that would still point in the original direction that you're trying to get at. So this is our acceleration that we're going to have here. So we're going to use Newton's law of gravity to calculate the acceleration. And if we put these ingredients together, it's going to look like state of the system will be the initial state plus this velocity times a time step. And this is exactly the same picture that we talked about with our one-dimensional case, except now it's six-dimensional. So this is state of the system. This is the initial conditions. This is our generalized velocity. And this is the time step. So this is, I realize this is kind of an abstract or math that you're maybe less familiar with, numerical integration. But part of why I wanted to show you this is because a lot of times numerical integration can be kind of a dry subject. And so I wanted to show you an example where you can use it to do something that's really cool. So we're going to use this to show what the how satellites orbit and connect with things like Kepler's laws. Um, and it's just a really a little more, I think, a little more of an interesting application than what you may have encountered so far. So the next thing is, let me show you the code. Okay, so you should see the code. I want to walk you through and show you a few things of interest. So the first section that I want to point out is where we set the initial coordinates and our setup. So you'll notice the initial state, x, is set here. It's got 6 pieces, x, y, z, and vx, vy, and vz. The other things that we need to set are h, which is the step size, the time in seconds, and steps, which is how many steps you're going to go through. So you'll notice there are some example situations that are already coded in here. The way that you run these is you just uncomment them. So if I, for example, if I go like this, it comments this, this won't execute. So if I want to run this example for the International Space Station, you would uncomment it, and then it will run. It's going to run whatever one is last. So for example, if I uncomment this one about IO, it's going to run IO and not the space station. If I comment this one away again, it will run the space station. If I comment this one away, it's not going to run anything because none of them are there. They're all commented out. But if I want to run the space station, so the stuff that I would need are vector, x, y, and z, and vx, vy, vz. So this is set so that the only component will be x, y and z are set to 0, and the only component of the velocity is vy. Because if you think about it, remember the velocity and the radius are going to be perpendicular to each other. So if I set the initial radius to be in x, the initial velocity can be in y, and those will be perpendicular. And these are in kilometers and kilometers per second. The step size that we're using is 60 seconds, and the number of steps is 120 steps. And then this is also setting the mass to be the mass of the Earth, because we're looking at a satellite that's going around the Earth. So let me show you kind of the next part of the code. So that's where you set your settings. You can change this to pick whatever system that you want to look at. So I put a thing in here, pick a system that you want to simulate. And I put this space station one here to start with, so you have something to kind of start with. Next, it calls the main function. So this is where the program, this is the main part of the program. And then there's some stuff to make some plots. So this will spit out how much time that you've done it. This is to generate the plot of the orbit. So the functions that this calls, this RK4, RK stands for Runge-Kutta. This is the kind of integration. So I told you about like the trapezoid rule. You can think of this as like a very sophisticated trapezoid rule. So this main program, it needs your initial state, and it needs the step size and the number of steps. So you can think of this as being like the loop. So you can see that it's got a for loop over the number of steps. So this is where you're looping in time. You're going forward in time. And this thing calls another program or another function, this one here. And this is what is doing the integration. So if you look at the next one, you'll just see it's got these different components. So the Runge-Kutta is more complicated than the trapezoid rule, which only uses 2 values. This uses more. So it makes a curve and it's more accurate. It's a better representation of the shape that you're trying to integrate. So that's why this is more complicated. And then the thing that I really wanted to point out to you is if you look in this function, which is called by the Runge-Kutta function, This is where you're calculating the velocity, the general velocity that I talked about. So notice this gets the state. The first part of the state is x, y, and z, and the second part of the state is v. So what it does is it says, okay, the first part is v, so it's using the previous one. And then to find the acceleration, it does Newton's law of gravity. So this is Newton's law of gravity right here. We have g, we have the mass, in this case, the mass of the Earth. This norm means length, so this is telling you the length of your displacement vector, x, y, and z, cubed, and then so we're dividing by the length cubed and multiplying by the vector. So like I said in the introduction video, this would be the same thing as r hat divided by r squared. So they have r divided by r cubed. And then this returns those pieces. So this returns the velocity and the acceleration, which is used in the integration. And that's the whole code. So you don't have to change the things that are in the functions. Those will work. What I want you to change is to pick a system. You can look up on Wikipedia or look, Google, and find a system. You'll have to input it into here. So you have to input its initial position and its velocity. And then you might have to play around with the time step settings to get it to plot an orbit. So hopefully seeing this code kind of shows you the parts. Let me run it for you so you can see what it looks like. So I'm just going to run, just going to click run section, and that'll just run the part that for the space station. So this is the orbit for the International Space Station. And then it's plotted also a circle that represents the size of the Earth. So this gives you a sense of how close the space station is to the Earth, which is kind of interesting. And you can mess with this. So for example, if I'm going to increase the speed of the space station a little bit. Let's increase it by 10%. If I do that, we can numerically integrate again and see what the orbit will look like. Now notice, this is cool. We didn't do a calculation. This isn't an analytical thing. We're using the program to tell us what's going to happen. And it's numerically figuring out that if we were to increase the speed a little bit, we make the orbit elliptical. So it's off center. It also takes longer. Look how it didn't come back. So normally the space station goes around the Earth in less, I think in about an hour. And so if we were to increase the speed, it's going to make the orbit change the orbit. So you can play with this. You can try different scenarios. But what I want you to do for the assignment is to, pick a system, a new system, look something up, and get it to work in this code.